Okay, so let's just start. Well, welcome everyone, and appreciate very much joining us for this January webinar for TRANS-IPIC. For those who don't know me, my name is Bassem Andraus, and I'm a professor at the University of Illinois, Urbana-Champaign. I'm also the director of TRANS-IPIC. It's my pleasure to be moderating this webinar here today. We have two excellent researchers, faculty members, colleagues who are working on excellent topics that they will share the updates about their work with us today. Before we start, I would like to give a quick overview of what's going on with TRANS-IPIC for the researchers just to get some updates from us. Of course, it was very nice to see some of you at the TRB event earlier this month. That was great. We had very good faculty meeting. We had very good, actually, number of presentations and posters representing the work done by TRANS-IPIC researchers. One of the things that I want to just again confirm that those who haven't heard, our list of projects that were selected for year 3 has been approved by the USDOT. That's an important step now that's required. So you are allowed to start spending actually on these starting from January 16. I know that the sub awards for some schools are still, the work is underway to be amended, the sub award from last year. If you haven't provided your paperwork yet and documents to Chris, please do so immediately so we can start amending your sub award. But you're allowed to start spending starting January 16. Anything expenditures happening January 16 and forward on that project will be approved. So that's one thing. The other thing also I want to remind you of is the upcoming workshop. We have our, of course, annual workshop scheduled April 14, the same venue in Rosemont, Illinois. It's one-day event. We reduce it from 2-day to one-day event because I know that travel sometimes is is an issue for some of our researchers coming from other states. So we have a list of speakers and, of course, posters. So the one thing we're having this year that is new is that we are going to be having sort of proceedings coming out of the workshop, which is a good thing. So it's a very short paper. I would call this extended abstracts, 4 pages. Essentially, the good thing about it is that it could really reflect the work that's being done in the project and also give the students something to cite in their CV or resume, documenting their work and presentations in the workshop. So there will be more information following up in the next maybe week or two about the template used for the paper and all this kind of stuff. I guess without any further ado, I would like to start by presenting our first speaker, Professor Eun Jeong Cha. Professor Cha is, of course, from the University of Illinois at Urbana-Champaign. She's an associate professor in the Department of Civil Environmental Engineering at UIUC. She holds a PhD and master's in Civil Environmental Engineering from Georgia Tech, and a bachelor's degree in architectural engineering from Seoul National University in South Korea. Her research focuses on risk-informed decision-making for civil infrastructure systems with emphasis on structural reliability, bridge and lifeline performance, and long-term infrastructure resilience. She's going to be talking to us today about environmentally informed, data-driven precast concrete bridge condition modeling for future-proof transportation infrastructure. So, Professor Cha, the mic is yours.
Thank you. All right. So I guess everything is sharing okay.
Yes.
Yep.
Sounds good. All right, Bassem, thanks for the introduction. So I'm going to present my recent work that I have performed together with my research assistant, Pranit, in the last year. focusing about the precast concrete bridge condition modeling, utilizing data mainly, and also the different types of data, and then focusing on the environmental data. Okay. Oops. Yeah. So the motivation of this work, we started from the bridge condition modeling, and this bridge deterioration is driven by many factors. And the most commonly, we consider the traffic data and then the structural information, the AGs and everything, but also the environmental exposure is also a main contributor that we need to consider. But some of the many existing deterioration models still relies on the coarse regional descriptors, especially in terms of the environmental data, or like historical averages, which can miss the local variability that the bridges experience, and also the environmental factors that can vary by time as well. It may be missed in those models. So we wanted to actually bring in those more detailed environmental data so that we can potentially improve the prediction and the decision making for the condition management for the bridges, especially the precast concrete bridges. So we wanted to see the differences as well between the bridge deck type. So our overall goal is to integrate the detailed environmental data set to better forecast how and when bridges deteriorate. So quick overview of today's talk. We streamlined this according to our modeling process as well. So we started with the data. So I'm gonna go over what data that we have used and what kind of processing of the data that we have done, and the initial model that we have developed, and some challenges that we have and how we actually tackle them, and also the model performance of this initial model. And then we also have improved this model. We are gonna talk about the model improvement, about the data expansion, and the variable selection techniques that we have used, and this improved model's performance. And I'm gonna also show you a brief demonstration of the model application in terms of predicting the bridge condition with the variable environmental scenarios. And lastly, I'm gonna show you a little bit of a comparison between the precast versus the CIP bridges, CIP concrete bridges performance. So for the data sources, so this includes all the data that we have used for both of the initial model and also the improved model as well. So we consider that we use the bridge data, traffic data, and climate data, and the sources are listed here, and there are different parameters that have been considered. And these are just some specific parameter, but the variable that we have used is statistically defined, and it's a little more complex. And I'm gonna show you that in the later slides as well. So for the data processing, for the environmental data, we consider the hourly and daily observations. So this is like some more specifics of what specific variables that we have considered. And for this current study, we have considered Illinois as our case study. So we use 4 Illinois weather station data, and we aggregated the annual variables. And there can be different ways of aggregating this data in terms of mean, maximum, the minimum values. And we also consider the temperature, humidity, precipitation, snowfall, heating degree days, cooling degree days. And there can be multiple years data. For this specific study, we have considered the 2022's data. And for the condition rating for this specific year, we could find 2,400 around 2,400 precast bridge inspection data, which has been compiled together. And the traffic data, we have considered annual average daily traffic and truck percentages for each bridge for the same year as well. So data mapping was done by linking each of the bridge to the nearest weather station. So all those data are all compiled together. And specifically, we actually consider the different years of data, but the year 2022 was chosen as it contains the most data points for the analysis. So the initial model was generated by utilizing two different modeling techniques. First one is multinomial logistic regression, and the second one is neural network multi-layer perceptron methodology. So multinomial logistic regression model has been chosen because it is simple and it also has very good interpretability in terms of the relationship between the parameters. And also the neural network has been chosen because we also wanted to consider the little nonlinear relationships as well. So in the initial analysis, these are some of the variables that we considered, and you can tell that this is not exactly same as what I have presented in the earlier data slides. So these are just a subset of variables that we initially started with to generate the baseline model. So for the multinomial logistic regression, it calculates the probability of a bridge belonging to a specific condition classes. We use two different classes. First one is a good, fair, poor, just a 3-class system. And the second one is the structural evaluation classes, that 9-class thing from 0 to 9. So those two are separately used, which we have just to generate a separated model for each individual of them. So we are, with utilizing multinomial logistic regression, what we can get is a probability of that the class that the bridge specifically belongs to. With utilizing x's are the parameter. Those are all the predictors that we use, which are coming from structural parameter, traffic parameter, and environmental parameters. Multi-layer perceptron architecture is what we see here is the final architecture, and we have used different cases, and this happened to be chosen as the final architecture that we use. So we have the different, so the size of input layer is 10, and the output layer is just a number of classes specifically, and there are 3 dense layers in between. So while we are modeling, so this modeling is, I think, something like design. It's not just done in one step, right? So we do generate the model, and then we test the performance of the accuracy of this model. And there are like lots of issues that we generate that we have found. And the one main cause of this issue that we have found is a class imbalance in the data set that we have. So as we can all expect, there are really not that many low rating, not the poor performance bridges actually out there, right? So when we see here in the table for the bridge condition rating in the poor, fair, great, the good rating, majority of the bridges belongs to the good rating, and we don't have much of a good representation for the poor rating. So there is definitely data imbalance, and that cause some of the issue in terms of performance of the modeling. And similarly, this just shows the decomposition of the data set again, but in terms of the structural evaluation rating from 0 to 9 scale. And as you can tell, the majority of the bridge data belongs to actually good rating over here, right? So class 9, 8, or 7 rating instead of like a lower rating, we see like almost non-existent data set. So to address this class imbalance, we have considered the different techniques. First one that we considered is oversampling of minority classes based upon our data. So when we are training our model, we oversample minority classes. And the second methodology is undersampling of majority class. They're kind of working together. So we randomly reduce majority class samples to prevent the model biases. So they're working together. And also the third methodology that we considered is assigning class weights. In this specific methodology, we penalizes misclassification of minority classes more heavily during the training. So this, in our cases, when we evaluated this assigning class weights, actually worked it the best to improve the performance of our model. So on the bottom over here, we have like how we have calculated the class weight based upon the ratios of those specific class data set compared to the overall that has been used, and then that is used as a penalty. So the coefficients multiply to the penalty to train the model in the end. So with using this technique, so we chose to use this class weight for training our model, and then our initial model. For that, we use the training to testing data split as a 7:3 ratio. And using both of those two methodologies, logistic regression and the neural network methodologies, we have gotten pretty similar result. For the 3 class rating, the good, fair, poor rating, we have gotten accuracy around 55%. And using the 9 class rating, we have gotten the accuracy around 37%. And obviously, we are not happy with this result. So we had to find additional the techniques to improve the performance of the model. So in this slide, we just see the decomposition of our prediction. So you can tell that over here on the left-hand side, this y-axis, you can tell that is a true value. And then over the different columns over here, that shows our prediction. And our prediction was mainly around that the majority class that we have shown earlier. And this is definitely not allowed. So we try to improve the model. First, we started with expanding the data set and then try to identify the more important key variables more systematically. So we added every individual data set, the environmental data set, the structural data set, and also the traffic data set. We are still using the 2022 year data, but we expanded the total variables from 5 to 37 of variables, and then start from there and started to identify the key variables. So this just shows all the data that we have. There's a name of the data that we have started to using. It doesn't mean that we are gonna consider all of them. We are not gonna include all of these parameters as predictors in our the data-based model. Instead, we are gonna go through one more step of a variable selection so that we can identify the key predictors that significantly improve the model performance while we are letting go of some of unimportant predictors or that is redundant predictors. So we utilize a stepwise backward elimination based upon the AIC technique. And then after performing this procedure, we have reduced this feature set from 37 to 10 variables. So this is around like a similar number of variables compared to the initial model, but these are different because that earlier model we just identified based upon just the literature review, but this one was actually selected based upon the statistical modeling. So the variables selected utilizing this AIC technique include the age and the load, design loads, and some of the environmental parameter. That's what we actually wanted to see to make sure that environmental factors are indeed the key factors affecting to the bridge conditions. So the model performance for this improved model, as you can see, for that the 3-class rating, it has been improved from 55% to 74%, quite impressive improvement. And for the 9-class rating, still it's not as good as that the 3-class rating, but the accuracy has been improved to 46% now. So this shows confusion matrices for this improved model, and this will be a little easier to see confirm the performance of the model when you see these 9-class cases. So earlier we have been mostly predicting the bridge condition as 7, the rating of 7, but now it is more distributed, the better distributed. So we can predict the bridge condition a little better now. Okay, so this generated model now has been applied to predict the bridge condition under different scenarios. So the environmental condition always varies, and we want if the environmental factor actually affects to the bridge condition, how much it's gonna change depending upon the environmental scenarios. So these slides summarize this investigation. Left and the right-hand side figures are technically the same thing, but it's just one from the left-hand side. This one is from the logistic regression model. The right-hand side is from the neural network model. We actually observed pretty similar behaviors. So the orange color represents the 2022 environmental condition, so just a current condition. And the blue color represents the 2050, the environmental condition, and the green represents the 2100, the environmental condition. And we have used IPCC RCP 8.5 scenario in this case, but we can consider any of the environmental condition in this case. And the 2100 is a little more severe environmental change case. And you see that the distribution along the different classes, the bridge rating here is shifted a little toward the left-hand side. It is a little bit more obvious to see on this right-hand side figure. So for the green, it goes more left. So we have more of the rating 4 and 6 than before. Lastly, we also generate, so all the models that I have been showing to you are only for the precast concrete bridges. And then now we also have generated a similar model by utilizing cast-in-place concrete bridge data as well, and compare the performance, compare how the bridge condition varies depending upon this deck type as well. So for this analysis, we regenerated the model utilizing XGBoost and the SHAP together. And we consider this precast and the cast-in-place deck type as the variable, and we switch them to see how the likelihood of the bridge being in a certain class changes if we change the deck type, while all the other parameter is fixed. So we have calculated, we have used the data set for the precast, the same data set that around 2,400, and for CIP, we have around 1,700 data. And what we see on here, on this diagram, we have done this analysis in depth, but we are just showing this one result. It shows the difference in the probability of a good rating for a bridge. And then we just take that difference as a precast minus the CIP. So which means if this delta probability is larger, so it is positive, that means precast bridges performs better than the CIP bridges. And we especially take a bin of the ages from 0 to 20 years, 20 to 40 years, 40 to 60 years. As you see here, it varies. And then for depending upon those age, we have found that this difference, relative performance of a precast bridges varies. That's what we have found. So we have found that these middle ages, 20 to 40 years, we have found that precast concrete bridges seems to be performing slightly better than the CIP bridges, but the other age criteria, the other age bins, we didn't find this specific behavior. So this advantage of using precast concrete, it may vary depending upon the life stage of these bridges. And the limitations of our research, we have used only 2022 year data, and we haven't considered the other data. So we are planning to actually expand our data set, longitudinal data set. So we are going to consider multi-year bridge data for more sophisticated deterioration modeling. And in here, we definitely need to deal with the class imbalance case. So we will need to dig into a little further to find a little better way of addressing this issue as well. And also in our current model, we haven't considered the maintenance history or intervention records, and they're really not that much that we could find. So that's another thing that we are trying to incorporate if we can find additional information for. So in conclusion, I have shown you a data-driven bridge condition model that integrating structural, traffic, and also the environmental parameters. And we have found that this environmental factor actually impacts to the bridge condition, and especially when we happen to have different scenarios, different environmental scenario that can actually change the bridge deterioration quite a lot as well. And we also have found that the bridge deck bridge deck type may actually affect to the bridge conditions as well, but a little more detailed analysis will be needed. And then all these bridge condition model can be used for the future the expansion and development toward long-term forecasting, the long-term management of those infrastructure systems. So that's all I have today. And if you have any questions, please ask now or send me an email.
Thank you so much, Dr. Cha. Very interesting work. Those who are in the audience, they can either raise their hand and they will be unmuted to ask their questions, or they can type their questions, whatever the way they feel comfortable doing.
I see one hand raised.
Yeah, there's one hand.
Should I unmute?
No, I did unmute them.
Yeah. Can you hear me?
Yes.
Yes.
So I have two questions. So first one is how the bridge condition rating, so which was from 0 to 9, was assigned in the dataset as response variable. And my second question is, did you break down those 5 primary variables to 37, and which was reduced to 10? Because if you do so, then there's a probability that the AIC selected those variables which are closely related.
Okay, so The first one was how it was about that the 9 class rating.
Yeah,
Okay, so how I got that?
yeah.
Okay, so these are not something that I came up with. So these are the actual the class rating that's used in the data, the NIB data. So we downloaded them.
Okay. So it was already present. Thank you.
Yes, that's as part of actual data sample that we have collected.
Okay.
And then the second question, can you rephrase it? I didn't hear you well.
Yeah. So you said that the 5 variables were extended to 37 when you did the dataset expansion, and
Uh-huh.
then when you applied AIC, those 37 variables was reduced to 10,
Uh-huh.
and then it increased your accuracy. So is it possible that how did you break down this? How did you expand this data set to 37? Like, did you break down the primary variables into 37 categories, or those are new variables that you inserted?
Right. So yeah, good. Thank you so much. So for that, the 37 variables, so these are more of like, yeah, we expanded from what we have earlier, and we actually perform a little more in-depth literature review to include, just come up with anything that's really can be related to the breach condition. So whatever that has been named at least one time in any literature, we included it. And then obviously the name of those parameters from the data set may not match to the ones from the existing literature. We just went kind of a wide search, expanded the first, and then obviously if you use too many variables, it doesn't always help to train the model. So that's why we just needed to identify only the key variables, and whenever there is like a redundant variable, we need to let go of them. So that's how the AIC works. But the earlier part, we just try to identify everything that we could find from the literature review.
Okay, yeah, thank you.
Right, any other questions, Dr. Cha? All right, and I have one quick question. So how far did you go back? Maybe I missed that in the presentation with your environmental data that you used.
For this one, we only use the year of 2022. So
Okay.
all the data sample that we need to match it, right? So we don't want to match the traffic data of 2022 with the 2000, the year of 2000, the environmental data. So in this case, we actually use the breach condition data as a hinge. So we just found the year with the most of the data sample, which happened to be 2022. And then for the generally environmental data, it's annually obtained. So we can always find the specific year of data as well. So that's what we have done. So we are going to expand this. So however, whichever year that we would have for the breach condition, we are going to match that with that specific year's environmental data so that we can actually do dynamic modeling with the breach condition, the variations over time.
Okay. Thank you so much. Last chance for any questions, Dr. Cha? All right. Well, thank you so much. Thank you, Dr. Cha.
Thank you.
All right, let's move to the next speaker, Dr. Yen-Fang Su. Dr. Su is an assistant professor in the Department of Civil and Environmental Engineering at Louisiana State University. Prior to joining LSU, he was a postdoc research associate at the University of Cambridge, where he collaborated with the UK's National Highways to implement 3D printing technologies and smart sensing systems for civil infrastructure, leading to the development of the world's first 3D printed smart head wall. He earned his PhD in civil engineering from Purdue University, where his doctoral research contributed to the development of the new AASHTO T412 standard. Dr. Su, the mic is yours.
Thank you. Thank you for the introduction. So let's share the slide first. Okay. I believe you can see my slide now, right?
Yes.
So yeah, thank you very much for the invitation. So today I want to talk about the work done with my student Kailula Touch on the 3D printed smart permanent concrete formwork for the precast structure members, structure components. So as we all know that 3D printing nowadays is a really a novel and promising technology because it can reduce the cost, potentially reduce the cost, and enable a lot of flexibility in terms of the design and might be able to reduce the time. So we come up with this idea that one of the most promising field for this 3D printing might be we can use a multi-material and to build the multi-material structures, specifically move from the for the people previously is for the polymer, and we are thinking why not we move for the concrete structure or precast concrete structure to enable the multifunctionality. And within this multifunctionality, one thing really catch out our eyes is the ability of the sense or monitoring itself's condition. So the reason why we are really into that is because as we know that if we want to leverage this technology and the current infrastructure, transportation infrastructure is not in the good shape, and if we want to build the new one or if we want to do the repair, and it's better to embed this structure health monitoring property or functionality. And for the cost of the structural health monitoring, typically for traditionally, we intro a lot of different variety type of the sensor. However, as you can see, the cost is not cheap, especially in terms of the cost, mainly from the sensor, different sensor, and also the maintenance is not cheap as well. And we are wondering why not we find out the material that can build the intrinsic sensing property or performance. So that leads us to study the self-sensing cementitious material or smart material. So in fact, this smart material or smart concrete is proposed by Professor Chung. I think Professor Chung is also in our center from SUNY Buffalo. So and we really appreciate she proposed this idea like a few decades ago, and we really into this material, try to understand if this material can really implement to our civil infrastructure for the large scale, because this material can sense the stress, humidity, or different change of the internal structure. So since this material is not cheap, and so we are targeting to embed those type of material to the specific type or critical area of the structure. So for just give you a brief introduction of the self-sensing cementitious material. So self-sensing basically is through the two mechanism, the electronic conduction and the ionic conduction. Electronic conduction is by incorporate the conductive filler to the cement matrix, and then we can obtain the signal, electronic signal from that. And the ionic conduction is based on the moving of the free ion in the pore solution, like intrinsically built in the cementitious material. Specifically for the high alkaline active material is like it's abundant. So but how self-sensing performance be measured? So here I give you the animation we produce, which is if we apply the load to the material, and we can use we can measure the electrical signal by shooting the current to the material and obtain the reflect impedance or the electrical signal and convert that to the frictional change in the resistivity. And then we further use this to calculate the strain gauge factor to compare with the strength or the deflection. So it's basically like the strain gauge, but it's to build in the material itself. But how to design the self-sensing material? This, as I said, this material has already developed in, proposed and investigated for a few decades, but however, it's all in the small scale. So we wonder for the large scale. So it's really critical to select the functional feeder or conductive feeder. And especially when we select that, there's one thing we need to take care of is the percolation threshold, which is we cannot make the material too conductive or make material to isolate. So we need to find a point but in between. So then we conduct a really comprehensive literature review from around 100 journal papers from 2000 to 2024 and collect some data to plot this gauge factor versus the strength. And we classify into the concrete, pads, mortar, and some UHPC. So we can see that the some result or some paper present really high gauge factors, especially for the concrete, mortar, and the pads. And in terms of the conductive feeder, we also noticed that people not only use a single type of conductive feeder, some people use a hybrid, different type of conductive feeder together, and some of them get extremely high gauge factor, or so. So we are trying to figure out what type of conductive feeder we're gonna use. Then we also organize this data, which in terms of we find out the conductive feeder can be also be classified into the 0D, which is a powder form, 1D the fiber form, and the 2D the like the plate. So and we found out that 1D and the 2D seems to be better compared with the 0D, so that we collect the material. We found the material for 0D, 1D, and 2D, and to try to make the self-sensing concrete and to try to see what's the result we can obtain. So as I say, for the 0D, 1D, 2D, we start from the carbon-based material. The carbon black is a 0D material, it's a powder form, and the mill carbon fiber is a 1D material, and the 2D material, we got the pristine graphene. We collaborate with the different company to source this material. And this table just show you the property of different conductive feeder, including the shape, the density, and the resistivity. The difference is large. So then we firstly come up with the mixed design. We use the ordinary Portland cement, silica film, and the sand and water to make the mortar because we want to target for the 3D printing and pilot testing first. And we add the mill carbon fiber, the pristine graphene, and the carbon black, try to see whichever is better in terms of a different property. So we start from the first stage. First stage, we start from measure the rheological property, including the flow diameter, setting time, shear strength, and the viscosity, because that is important for the 3D printing. And we also test the mechanical property, including the compressive strength and the interlayer bonding strength, because the compressive strength, of course, is going to be really important for the infrastructure, and the interlayer bonding strength, because we are thinking about it's going to be the permanent formwork. So we're going to have the formwork, and then we cast the concrete. So this bonding is really important and essential to make sure the integrity of the structure. Later, we test the self-sensing property for those materials. And next, we move to the second stage, test the 3D print small scale pilot sample, and then we use the robotic arm developed in our lab for the large scale, and we move one step further to the to test the environmental effect including the temperature and the humidity. So we first found the rheological property of the self-sensing concrete cementitious material. So for this flow table testing, it shows that for the sample with the carbon fiber, it got a pretty good or spreadable, workable flowability, and as well as self-sensing cementitious material include the pristine graphene. However, we noticed that the carbon black actually absorb a lot of water if we use the same water to by the ratio for all of the materials. So you need to adjust the water in order to achieve the flowability. And for the setting time, because that is relevant to the opening time and also the printing, the stiffness development of the 3D printing. So we found out that the carbon fiber and the pristine graphene all behave great, which has a longer setting time compared with the carbon black. So for some mix we design with 5% or 3% of a carbon black, its setting time is actually pretty quick. And we further want to identify what is the printing zone or printability region. So we do the viscosity testing, identify the zone over here, and also shear stress, which between these two lines is the printing zone. And for the mechanical property wise, we prepared a cube sample for 28-day testing. So for the compressive strength, as you can see, if we add 0 like conductive feeder, the strength is around 5,000. But if we add a small amount of the mule carbon fiber, it actually improves the strength. And so does for the pristine graphene, until if we add too much of a pristine graphene, it might cause agglomeration and lead to the low compressive strength. And however, for the carbon black, it's not behave as good as the previous two material we incorporate. So for the bond strength wise, which is really important for this formwork, for the reference, we got 194, and if we include the carbon fiber, we got as high as 300 for if we include the 0.05% of the carbon fiber. And we also got the good performance from the pristine graphene. However, for the carbon black, because for this 3% and the 5% of carbon black, the mix is too dry to bond to the other structure. So we got no data, but apparently it's lower. So we also want to measure the self-sensing, of course, the property, and this is the configuration of our setup, and we use the four-port method to avoid this the bad signal, and we apply this 20% of the FC plumb to our sample, and for this cyclic loading for 10 cycles. So first we start from the 0D material in terms of the carbon black. As you can see, for the control set, we got almost no signal for this FCR. If we incorporate a small amount of carbon black, we can see some signal, especially for the 1% for the carbon black. We see really a significant signal. And if we add up to 0.5%, we got really noisy signal. Then we switch to the 1D, this mule carbon fiber. So mule carbon fiber, in fact, perform better, especially for this with CF05, 0.05%. So it got we got more stable and obvious signal from this mix. And for the 2D, if our material incorporate this 2D pristine graphene, surprisingly, we got really not the really subtle signal out of these samples. Only PG with 0.1% got a better signal output. So our guess is this type of material, this pristine graphene, if that is not dispersed well, and that might cause the signal cannot reflect its change of the structure behavior. So we further move to evaluate the stress sensitivity, because if that is sensitive enough, then it will be great for structure health monitoring. And we found the CB01, CB05 give us a better, really great signal, as well as a CF05. However, as I mentioned before, for the sample incorporate the carbon black, and the rheological property as well as the mechanical property is not as good as the sample incorporate the mule carbon fiber. So we determined to use the mule carbon fiber mixture for our 3D printing purpose. And in terms of the 3D printing, we firstly try some small sample, try to figure out if that work, and with different printing configuration. As you can see, we have the MOLCAS. We compare the MOLCAS with the with all reference mix, which in terms of the gray, and the green refer to the sensing mix. And we also print the shell and grow with the concrete inside, and try to understand if that is we can see the good signal to compare that. And also we try different configuration, because as we say before, this special material is not cheap compared with a conventional concrete. We want to reduce the cost, so we end up design a different mechanism, including this. We put only printing mix in the middle of the structure, and we also have another set which is we split that in two separate sections. And furthermore, we also want to investigate if we just print a small core inside a structure, if that works as well. So this slide shows you the result. Apparently, if we incorporate this self-sensing concrete, we can see the change of the signal along with the cyclic loading. And for the formwork, 3D print formwork, we can see really good relationship between the cyclic loading, and the gauge factor is around 10. And we also find out that for this P2, if we only incorporate this material in between, in the middle of the structure, we can also observe the signal. And in the middle, as internal core, we also obtain a good correlation. So in terms of to reduce the cost, and we determined to go for this configuration. So for the larger scale, using the printing. So this video just show you the robotic printing in our lab, and we have the in-house developed the extruder and the system, and the students working on incorporate the electrode. Yeah, so 1/3 of the for this entire structure, the top and the bottom 1/3 are a regular control mix, and the middle 1/3 is the CF0.5 mix, and we also test its 28-day strength, and the strength is not bad. It's around 6 KSI. So we then we conduct this low the self-sensing evaluation with around 15% of the load rate, and we can successfully obtain this change to reflect the cyclic loading. And we want to move one step further to discuss the environmental effect. So, as previously Dr. Eun says, environmental is really important to our infrastructure. So, we firstly start from the different humidity level. And the thing is, once we cast the sample, then we submerge the sample all the way to the water for 2 days, and to make sure it's in the saturated surface drive condition, SSD condition. Then we also measure and then we put into the oven to create the different humidity conditions. As you can see, it's a time versus the weight. So we put into the oven at 60 degrees of Celsius for 12 hours, 24 hours until 48 hours. So as you can see for the SSD, if you are fully submerged and the humidity is 100%, then you got a lot of noise, and which is really hard to interpret. And if you only drive for 12 hours, still the signal is not obvious. But if you drive further to 24 hours, we can start to see the trend of the cyclic loading. And for 48 hours, and we got a better signal. So we further convert that for the previous slide, that is the resistivity. We further convert that to the FCR, and then calculate the stress sensitivity. So apparently the 24 hours and the 48, specifically 48 hours, give us the better sensitivity. And for the temperature wise, we test 2 different temperature for the pilot study, 22.2 degree, which is the normal temperature, and 60 degree. And we observe that if we increase the temperature, the self-sensing performance actually decrease. And yeah, here shows you the stress gate sensitivity. So in conclusion, we for this project, we identified that the meal carbon fiber is a viable candidate to be used as a conductive filler, specifically for this 3D printing scenario. Its rheological property, mechanical property are really great, and also with high sensitivity. So, and we successfully achieved this 3D print Formwork, and we further test different moisture content, and the height sensitivity we obtained is around 12% per KSI for the 40-hour drive, and for the high temperature, it will reduce the resistivity significantly. So that will be used for the further investigation or study for the large scale. So I want to acknowledge the TRANS-IPIC to give us the opportunity to work on this project, and also we work closely with our Louisiana Department of Transportation and the Research Center on this. And thanks for the donor for the material, and that's our students. Thank you.
Thank you so much, Dr. Shu. Very interesting work. I think I see one hand raised. So there's a question.
Yeah.
Yeah, Dr. Chung, please go ahead.
Okay. My question is, your resistance seems to increase upon compression. Is that correct?
Yes, we observed this.
Yeah, that is opposite. to what
Yeah.
the because it is deformation or strain causing the piezoresistivity. The resistance should decrease upon compression. So, what is your explanation of your abnormal effect?
So, thank you, Professor Chung, for this question. So we are observed this for a while. We try to change the configuration, and then we have another study try to do like DC, AC, and our hypothesis is probably the polarization. That's something happened for these electrodes. So and my student, we are working on different, try to figure out different parameters, including the different, as I say, AC/DC and the different current and different configuration. And we end up, for this study, we use AC, but we end up figure out maybe DC can give us more stable signal.
I don't think that approach is going to give you the answer. I have played with all this polarization AC for a few decades. What I believe is causing your abnormal behavior is that there is some degradation, either within the material or at the interface between the electrode and the cement-based material. And degradation can be reversible. You know, it's just like crack closing and crack opening. Degradation can be reversible, and you have a reversible effect. But it's related not to strain, but it's related to some form of irreversible microstructural change or irreversible damage.
That make a lot of sense. And so in the future, I think the other approach we can try to figure out is the configuration of these electrodes and the contact between the electrode and the material itself. That might be something we can dig into in the future. Thank you very much for your comment.
All right, thank you. Maybe one last quick question to Dr. Shu, if there's any. Okay, well, thank you, Doctor. Well, there is one quick question here. I see a couple, okay. Maybe we can start with, Ishat.
Good afternoon. Can you hear me?
Or Samer, either one.
Yeah,
my
quick question on, you have done several molds, one with 3D printing, one with the regular, which is not using the 3D printing. How comparable those molds together? And can I use a regular mixer in the lab, that one that has a motor, the old-fashioned making concrete, to make a similar mold to the one produced by the 3D printing?
Mold. So let's switch to, so if I understand correctly, you are asking about the
duplicating the molds you've done with the 3D printing in a regular lab that doesn't have a 3D printer.
Doesn't have the 3D printer. Yeah, I think that is repeatable. Yeah, so if you can design the mold and then to produce this formwork, I think that might works as well. But we haven't tried that. But it's a really good comment suggestion. We might dig into further.
Okay, I'm looking for scalability where really 3D printing is more as a lab sample size, but on a large scale, it is not yet at the point of a 3D printing to be used at that level yet. So a regular mixer would be still the common one to make in concrete. So how could I produce what you propose today on a larger scale? That was the question.
In the larger scale. So in the larger scale, you mean mixing this type of material?
Correct.
In the larger scale?
Larger scale, yes.
Yeah, I think if we want to mix in this material in a larger scale, I think we need to specifically for this carbon-based material like a male carbon fiber, we need to first distribute that into the water and make a solution, and then we can directly dump to the ready-mix truck for the large-scale application. So I think we right now we are still in the lab trial, but in the future we might planning to do that, collaborate with the ready-mix company and to try to if we can use the material, dump the material directly to a ready-mix truck and to make it large scale.
Thank you.
Thank you.
I believe there's one more question. Ishad, yeah, maybe one left. Yeah, quickly if you can, please.
Hello, Professor. Thank you for the presentation. Actually, I am curious about the interface bond stress that you presented in slide 17. Like, is it between the two layers of the self-sensing concrete, or is it between like one self-sensing or normal concrete? Because I am curious about the governing behavior between the normal concrete and SSCC when it will be used in construction applications.
Yeah, thank you for the question. Yeah, so what we did is we cast the normal concrete first and cure for 28 days or longer, and then we put the self-sensing concrete on top of that to test if we can get the bond strength. So it's the normal concrete with the self-sensing concrete.
Oh, okay, Professor. Thank you. Thank you.
Thank you.
Well, thanks to both speakers, Dr. Cha and Dr. Shu. Thank you so much for your time and for giving excellent talks today. I'd like to thank you all for being with us here today, and we look forward to seeing you in our next webinar. Stay warm and safe, everyone, and see you next time. Thank you. Bye.
Thank you.
Thank you.
Thank you.